Good morning to all the distinguished guests and dignitaries who have joined us today for the celebration of National Science Day 2022. We are honored to have with us various eminent scientists who are experts in their respective fields and have willingly agreed to share their knowledge with us. Also, with the blessings of our Honorable Founder President Sir, Chancellor Sir, Vice Chancellor Ma'am, and others, we would like to begin our today's program. We begin this special occasion with the lighting of the lamp and the Saraswati Vandana to take the blessing of Goddess Saraswati. That was truly divine. National Science Day is celebrated to mark the discovery of the Raman effect by the Indian physicist Sir C.V. Raman on 28th of February 1928. For his discovery, Sir C.V. Raman was awarded the Nobel Prize in Physics in 1930. The theme for National Science Day 2022 is Integrated Approach in Science and Technology for Sustainable Future. I would now like to invite Professor Sunita Ratan Ma'am, Dean, Science and Technology and Director, Amity Institute of Applied Sciences, to deliver the welcome address. Ma'am, please.
Thank you so much. Honorable Vice Chancellor Ma'am, Professor Balvinder Shukla, our guest of honor, Dr. Shiv Kumar Sharma, Professor, University of Hawaii, Dr. V.K. Jain, Distinguished Scientist and Vice President, STIF, HOIs of Science and Technology, departments, faculty members, students, and all the participants. A very good morning. At the outset, I extend a warm welcome to all to the inaugural session of National Science Day, February 28. The day scientist C.V. Raman invented his game-changing Raman effect in 1928. Raman effect is a spectroscopy phenomena discovered by Raman while working at the Indian Association for the Cultivation of Science Laboratory in Kolkata. Actually, Raman effect describes how the wavelength of light scatters when deflected on a particular object. Raman won the Nobel Prize in Physics for the historic discovery in 1930. This was an important discovery that paved the way for several future scientific developments. The National Council for Science and Technology Communication approached the center in 1986 to designate February 28 as National Science Day, and the first National Science Day being celebrated on February 28, 1987. National Science Day pays tribute to the iconic physicist and calls on the Indian youth to follow in his footsteps. Every year, National Science Day is celebrated under a specific theme. This year, the theme of the National Science Day, launched by Union Minister of State Science and Technology, Dr. Jitendra Singh, is Integrated Approach in Science and Technology for Sustainable Future. It is the integrated approach in science and technology for sustainable future, which will help us to come out of a culture of working in silos to play a leading role in the global arena. National Science Day is the occasion to take a pledge and work with the integrated approach henceforth for sustaining livelihoods, sustaining human life, and for India to emerge as a leader in science. At Amity University, all the institutions under engineering, science, and technology have joined hands to celebrate this occasion through organizing guest lectures by eminent speakers, research presentations by the research scholars, and organizing various quiz competitions among students. The program is being organized through 4 parallel tracks organized by different institutions along with an evening talk. I take this opportunity to extend our heartiest and profound thanks to our revered founder president, Dr. Ashok K. Chauhan, whose keen interest in research always give impetus to such type of events. We are grateful to our Honorable Chancellor, Dr. Atul Chauhan, for encouraging us and providing us the best of infrastructure for online organization of these events. We are deeply grateful to Dr. Balwinder Shukla, Honorable Vice Chancellor Ma'am, for guiding us during the planning and formulating the program schedule. Her unflinching support has always been the driving force behind such endeavors. I'm also thankful to all the distinguished HOIs who have been here, including Dr. Nagpal, who are gracing the occasion. Once again, hearty welcome to all the participants and hope that we celebrate the National Science Day in its true spirit, and would conclude with a quote of legendary Dr. C.V. Raman that the essence of science is independent thinking, hard work, and not equipment. When I got my Nobel Prize, I had spent hardly 200 rupees on my equipment. C.V. Raman, unquote. Thank you.
Thank you, ma'am. I would now like to invite Professor V.K. Jain, sir, distinguished scientist and professor and vice president of ASTAIF, to also welcome the August gathering and say a few words. Sir, please.
Thank you very much, Honorable Vice Chancellor, Dr. Balwinder Shukla, Dr. Professor Shiv Kumar Sharma, Dr. Sunita Ratan, my colleague, Dr. Abhishek, all HOIs, my other colleagues, students, and all other speakers in the different tracks. I welcome to this great day. Apart from all this about Raman, as Dr. Sunita Ratan has told, this when this came to me that who should be invited to give this lecture, this is a matter of pride that immediately it came to my mind to invite Professor Shiv Kumar Sharma. Nobody can be better than that, because a person, he is from India, and he is working for last so many, more than 30-40 years at USA, and his specialization is Raman spectroscopy. So he has developed a equipment model in his lab, and it is a matter of pride that based on this this model, NASA they have made a complete model with the SuperCam, and now this SuperCam is landed on 21st. This is March 21st, and it is working to analyze the soil of there from a distance of 60 meters. So I thought nobody can be better to invite in this, who can give a lecture, a Indian born professor, developed waste equipment on Raman spectroscopy, and now NASA has adopted and it is working on Mars. So it is a, we are thankful to Dr. Shiv Kumar Sharma that he has accepted our invitation. When on this new year, when I got a mail from Dr. Sharma that his equipment based, this is on Mars and they are getting a very good results, and it is analyzed by different countries and all, and even the publication which they are coming, they are authors about 170. So it is a big program. And it is a proud that his equipment is there. So this, as soon as I got the mail, I thought, why not he should be give a lecture on this 28th or the National Science Day. So this is this one, and he is a PhD from IIT Delhi, and it is lucky that at that time we were together at IIT Delhi. It's a long back in 70s. After that, when we have organized a special conference under the Make in India program in 2015 at Amity University, only we have invited a large number of NRI. And I think about more than 40 people came from abroad. Everybody was ready to help that, yes, we want to help our nation. At that time, we have made Shiv Kumar Sharma as the honorary professor to Amity, and now he's honorary professor to Amity. This is a great honor to us. And after this conference, we have also provided that any honorary professor, he is coming to India, he will try to spend some of the time to the Amity University so that we all can be benefited, our students can be benefited, research scholars can be benefited. And he came about 3 years back also and spent about 7-8 days with the Amity University. So this is a great thing. And this one in, about this one, whenever we have asked any support from there, he has always told that any student, any faculty member, this one. So this is a great honor. And I tell that this is not only a lecture from an Indian scientist to USA, but it is inspiration that how this has been happened, that our Raman effect and Professor Sharma. So it is an inspiration to all our faculty members, young research scholars, everybody, so that we can work together. And he has always told that whenever you need any help, they are to give. With these words, I also welcome all the other speakers who are coming lectures giving in this different text. Thank you very much.
Thank you, sir. Honorable Professor Balwinder Shukla, Vice Chancellor, Amity University, Uttar Pradesh, is a strategist, an institution builder, an inspirational leader, and a recipient of many honors and awards. We would now invite her to address the gathering. Ma'am, please.
Our guest of honor, Professor Shiv Kumarji, University of Hawaii, the Honorary Professor of Amity University, my colleague, Professor V.K. Jain, Distinguished Scientist and Professor, and the Vice President of ST, Professor Sunita Ratan, Dean Science and Technology and Director of Amity Institute of Applied Sciences, all the heads of institution, faculty colleagues, students, and all the participants. First of all, I would like to welcome all the participants, our distinguished guests of honor. On behalf of our Honorable Founder President, Honorable Chancellor, and on my personal behalf, on this National Science Day celebration, and which has been being celebrated since 1987, when the Dr. C.V. Raman has discovered the Raman effect. It has a, the Raman effect has a lot of applications. You name any industry, you'll find this some application or others. The major applications it has in the pharmaceutical and cosmetic industry, geology and the mineralogy, or the gemstones, the carbon materials, the semiconductors, life sciences, paint industry, and many others. So therefore, this is uh, an innovation for which Dr. C.V. Raman has got the Nobel Prize also in 1930. But the important is that an innovation, how much it can change the life, day-to-day life of a common person, how much it can generate or create the industries and contribute to economics. Our Honorable Founder President, Honorable Chancellor Dr. Atul Chauhan have always emphasized to focus on innovation, whether it's academic innovation or the scientific innovations or any process innovation, because then only the things can improve. And the science and engineering innovation is the most important today if you really want to improve the life of the community or the society and also contribute to the economic development of the nation to make it Atmanirbhar Bharat. And I'm sure that our faculty colleagues have been doing a lot of innovation and the recently um, this national expo which is going on, and we have also put up our exhibition, and yesterday the honorable minister was at the Amity stall and he was highly impressed by the kind of the innovations Amity University have done. So it's important that it's not the just to teach the science. It's important how we can um, every day see the kind of the issues, the problems or aspects are there, how we can improve the lives of the people, or how we can bring the innovation which solves the problems of the industries. So I'm very happy and impressed by the planning which has been done by the science, technology, life science, and biotechnology, and all the domains of technical domains who have put up the wonderful program in the 4 tracks for the whole day, and whether it is going to be, and the kind of the scientists, the researchers, and the presenters have been invited. I'm sure that all the participants will have a great deal of learning, and which they will apply their learning to the day-to-day life, and also in the apply for the finding the innovative solutions. So with this, once again, I congratulate the organizing team, and I once again warmly welcome our guest of honor, Professor Shiv Kumarji, University of Hawaii, and also who is the honorary professor of Amity Universities. Once again, many, many congratulations.
Thank you, ma'am, for your words of wisdom. Thank you, ma'am, for your words of wisdom and encouragement. I would now like to invite Professor Shiv K. Sharma, who is a great Indian-born scientist and also an honorary professor of Amity University and has a specialization in Raman spectroscopy and has developed a new and a very important equipment to analyze the Martian surface. Professor Sharma's design prototype, time-resolved Raman spectrometer, is a time-resolved Raman spectrometer equipment is a part of the SuperCam instrument on NASA's Perseverance Mars rover and has landed successfully on land of Mars on 18th of February 2021 and is doing an excellent job on Mars surface. A prestigious moment for all the Indians too. It's a matter of great pride that an Indian professor based on his developed equipment on Raman effect and his system is working at Mars from 2021. Sir has been awarded the Best Paper Award for Remote Raman Laser-Induced Breakdown Spectroscopy by SAS in 2020. And till date, Sir has published over 200 papers. We are honored to have you, sir. I now request Sir to please share his valuable knowledge and broaden our horizon. Sir, please.
Thank you very much. And I think I will share the screen and see if it works. Can you see it, please?
Yes.
Yeah, okay, thank you. So what I'm going to do is to briefly show you the development was going on for University of Hawaii, and also briefly give you the history of the Raman spectroscopy, as it may be helpful for some young students. So here are the outlines. As previous speakers I mentioned, that the C.V. Raman discovery of elastic of light really revolutionized many aspects in scientific field. And then I talk about the planetary exploration on Mars, and the first laser-based instrument on Mars was a CAM instrument. It has only the laser-induced breakdown spectroscopy that provides the composition of the rocks and minerals. And then we came with the SuperCAN instrument in 2020. And it has 4 techniques, 3 active laser-based techniques, the time-resolved Raman, LIFS, and laser-induced fluorescence, and the passive visible infrared spectroscopy, and a microimager. So the instrument developed at University of Hawaii, we started with a fiber optic coupled time-gated stand-up Raman system. And then we went to the directly coupled system. And then we have a dual pulse 530 nanometer Raman lift system. And then we had a planetary compact gate-able Raman laser-induced fluorescent and lift system. So we combined all the 3 techniques in one. So it was nice to see that it was taken up by my colleagues, and they developed a system which is space qualified, and now it's on Mars. So I will summarize some of the results and finally the summary of the talk. So here is Sir C.V. Raman during his presentation at the Nobel Award in 1930. And so basically what happens is, if you take a monochromatic light, then you get a light of the same wavelength, and then there was a wavelength of the scattered light which was different than the monochromatic light. And this effect was not known previously, and the elastic scattering of light was known by Lord Rayleigh, and it is responsible for blue color of the sky and the ocean. So this was really a new discovery. And Raman published a paper in 1928 saying it a new type of secondary radiation. So after the Nobel Prize, they named it after his name. They called it Raman effect. So, so the scattering of light. This is the energy diagram. What happens is, if the molecule is in the ground state, it can go to a metastable state and come down to the same place. That will give us the so-called Rayleigh scattering. Now, if the molecule is excited to the metabolic state and come down to the first vibrational state, it lost that much energy. And if the molecule is in the excited state, comes down to the ground state, it gains energy. So this is called Stokes Raman shift, and the other one is called anti-Stokes Raman shift. And so it really involves the polarizability of a molecule, electric field of the molecule, oscillate at the frequency of the incident wave. And if induced dipole moment constant, is scattering, elastic scattering, the Rayleigh mean scattering. If induced dipole moment is not constant, then elastic Raman scattering is allowed. The very important thing is the lifetime of the Raman scattering is very, very short. It's like 10 to the power minus 13 seconds. So in the Raman spectrum, the information from the vibration of molecules is often the visible part of the spectrum as a difference from the energy of the visible laser excitation. So Raman spectrum is complementary, but the selection rules are different. For IR activity requires change in the dipole moment, whereas the Raman scattering takes place when there is a change in the induced dipole moment. So here is an example of selection rules. The polarizability is proportional to constant of the induced dipole moment. So in the case of CO2 molecules, if the vibration is a symmetrical stretch, there is no change in the dipole moment. And if it's asymmetric, then this is change in the dipole moment. So what happens is that the symmetrical stretch are active in the Raman and they are inactive in the infrared. The bending mode is inactive in the Raman, is active in the infrared. Asymmetric stretch is inactive in the Raman and active in the infrared. So a rule of thumb is that the centrosymmetric molecules or crystals in Raman and IR activity are mutually excluding. So that is the one of the rules of the things. So the question is why we are, how to measure Raman spectrum and why we need to measure Raman spectrum. So with the development in technology, the things are really miniaturized. So there's development of a notch filter, which suppresses the Rayleigh scattering from the laser. And then you can have a sample of any form. It could be liquid, solid, or gas. And then you have a CCD cameras, and you get intensified CCD camera that are capable of even detecting single photons. Now, in the Raman spectrum, the information is about the vibrational modes. And it is depend on the reduced mass and the force constant, and atomic mass is bond length, bond strength. And so every substance have a unique Raman spectrum. We call it Raman fingerprints. So the Raman fingerprints chemical detection with very high confidence level. So even the chemical composition may be the same, but if they are different polymorphs, like in the case of calcite, here another polymorph called aragonite, you can see very distinct spectrum. So what are the pro on this case is the no sample preparation, in-situ measurements, non-destructives, sample can be solid, liquid, gas, transparent, opaque, well-resolved data with high information content. Data can be measured in low frequency region with a single spectrograph. Measurement can be made in presence of water vapor or liquid water, as the Raman of water spectrum is relatively weak. The Raman signal is very weak. That's the problem. So I got one photon in 10 to the power 7 will be Raman scattered, but with the advanced in detectors and laser sources, the Raman signal can easily be detected. So that is the main thing about that. So we developed instrument at University of Hawaii. It started with the system here. This is just a prototype, and then we have a spectrograph, mini ICCD camera here, telescope is a camera lens, a 5x beam expander, and these are mirrors, and dichroic mirrors, and using a double 532 nanometer pulse laser with 30 millijoules of laser power at 20 hertz. So, and this is reported in 2015. And then the latest one is by one of my graduate students, and she did it to up to 120 meters. Raman system with 0.2 meter telescope. This one we actually developed mostly for the defense application, basically detecting the IEDs and explosives from a distance. And this has been tested up to 430 meters range. So the laser-induced breakdown spectroscopy called LIFS. So if you focus a laser beam and the intensity of the laser exceeds certain limit, then it breaks down the material and it evaporates a small amount of material, and then it goes to the excitation of the plasma with the later part of the laser pulse, and the plasma expansion stage, it will emit light and collected by the spectral analysis, and the cooling of the plasma and ablation crater is just like that. Amount of material sublimed is in nanograms limit. So, so relatively, you can say it's a non-destructive. So that gives you atomic spectrum, and it gives you all the elements in the periodic table. So that can give you the chemical composition of the system. So the laser-induced fluorescence is shown here in the energy diagram. So in this case, the energy of the excitation has to exceed the vibration levels. So it goes to the excited state and either go to S1 or S2, and then it decays thermally, and then it comes down and come down to ground state. And in the case of fluorescence by biological molecules or with the organic molecules, it is really very short, 10 to the power minus 9 to 10 to the power minus 7 seconds. But in the case of minerals like transition metal ions or rare earth ions, it is delayed because it has to check in the change in the spin. So it can be like in microsecond to 10 to the power 2 seconds. And so this is the difference in lifetime can be used for detecting the different type of trace element may be present, and also it can be minimize the interference of the fluorescence in the Raman spectrum. So the planetary explanation with active spectroscopy techniques, as I mentioned to you, the first active laser source on Mars was in the called CAM on the Curiosity rover, and it was operating since August 2012. The size of the Curiosity rover on Mars Science Lab is about the size of a small SUV. It's 10 feet long, not including the arm, and about 9 feet wide and 7 feet tall. The arm reaches about 7 feet. The weight of the rover is about 200 pounds. Now, far exceeding its initial planned mission for 2 years, the Curiosity rover is still active at the red planet in 2022. So it seems like the laser is doing a good job, and the spectrometer and all that. So since this was going on, there was an announcement by NASA to have a next rover mission, and they wanted to have the capability of finding the real polymorphs of minerals. And so my colleagues approached me and he said, well, can you join us anyway? So that is the story. So this is the CAM collecting cumulative laser shots, and like 500,000 was the Sol 1822. One Sol is 24 hours, 39 minutes. Is 2.7 times longer than Earth's day. CAM has returned about 400,000 spectra with me 2017 and greater than 12,000 observation. By May 28, 21, it has returned 880,000 individual spectrum, each representing a single shot from 3,000 different targets and more than 16,000 images. So the production and the information it is providing is really tremendous, and it's very, very popular with the scientists working on the planetary mission. So here is the SuperCam. This is one of those project development report. So basically, we combine two beams, the green beam for doing the Raman, and then the red beam was for doing leaves. And this just shows the scanning on different things. The question is that you can't really climb there, so the remote techniques allow you to look at things which are not easily approachable. So the PI is Roger Wiens from Las Alamos National Laboratory, and it's a collaboration with France, Sylvester Maurice, and is the deputy PI, and I am one of the co-Is from University of Hawaii. So this is a basically schematic diagram. The mast rotates, it can get elevation or azimuthal, And there are calibration targets just to see what the things are. The pressure on Mars is low, 1/10 of the atmosphere of the Earth, and it's mostly CO2. And so we need a calibration target to make sure everything working fine. And there is also a small microphone there, and it was initially used to find the sound produced by the leaves on the target. But it turned out to be very good for measuring the sound of the winds, and so it's also providing information about the dust storms and other things as well. So this is the mast unit, and there's a body unit, and they are connected by the optical fiber. So this transmission spectrograph, and this was designed after the work we did at the University of Hawaii. And this is interesting. They are just connected through optical fiber, which was the work we did back in 1989. So, and this is published in spectroscopy. So there is a synergy in all these techniques. So the leaves provide the elemental composition, Raman and fluorescence provide the information about the minerals and organics, and then the visible infrared provide the information about iron-containing minerals. So we get petrology and the effect of solution, aqueous solution, and organic preservation on Mars. So here is the scale showing the leaves as less than 10 meters. Raman is about 10 meters, and the visible infrared, it can go to kilometers range. So in this case, this is a positive technique, and it has to work in the sunlight. And so, and the photons are free, so that can do a long distance measurements. So information we get, this is a spectrum of calcite. And then you get, sorry, gypsum. So you get the laser here, and then you get the sulfate peaks here, and then this is a symmetrical stretching mode, and then you get the leaf spectrum. So got iron, and then silicon and magnesium, all these elements show up. And this is a visible infrared spectrometer. There's a color here. This is the pyroxene. It's a chain silicate, and then the phyllosilicates and the carbonates show up here, and then the polyhydrated sulfates. So, so you can see composition of the minerals on a scale at a long distance as well. So I just got some key papers which was started back in 1998. It takes time to develop new technology. Before that, most of the Raman instruments, even now, they operate in dark rooms because they're using a CW detection. So this was the first time we showed that you can do with a pulse laser the Raman analysis. And so that was the starting point. And then we had a measure to 66 meters in 2002, and so on. Then Roger Beans came up to University of Hawaii. He from Los Alamos National Laboratory. He has some problem in his lab, but they can't measure it. So he had a project. He said, "Can he come over and work with us?" I said, "Sure." So we discovered that you can do Raman and leaves together. And the idea is when you focus the laser beam, there is a the beam expander is not achromatic, so it focuses the green laser first, and then after that the 1064 laser. So by the time you focus 1064, the diameter of the laser beam is twice as large. So you can get the Raman from outside and then get the leaves from the central part. So that was very interesting. So we did some fluorescence measurements, and then I gave a talk at in a remote Raman spectroscopy. We did the combined Raman and leaves spectra. So some of the minerals are coated with the hematite, and the leaves can remove the hematite layer, and you can do nice Raman spectrum. Then we developed a scanning remote Raman system, and can do the large area and like that. And our group has developed a called a standout biofinder based on the fluorescence, short fluorescence. And then this one of the graduate students, he did on the mineral rocks. And this is my other graduate student who finished last year. That was the thing. So here is the system, which is, it's a dual pulse laser, 530 to 15 hertz. As I mentioned, it is actually used for using the most of the work for the Department of Defense. And so it is patented in US. This was the first time what we did with these high throughput volume phase holographic grating. And so the range was 450 to 850 nanometer. And so what we did, we stack up the 3 gratings here, same spectrograph, and then we were able to extend the range. So here it is, you can see 1, 2, 3, 4, 5, and these are the different spectral range. And then by integrating along the lines, you can get a spectrum. And this is the spectrum of iron. And so that's how it worked. So we did 100-meter test with this one. The sample is far away. This is the College of Engineering building. It's like 120-meter long corridor. And so to see if it works well, so it did work very well. So here is the spectrum of the laser excitation is there. And then we get the spectrum of nitrate at 9 meters and then the with a 25 millijoule pulse. And these are single shot experiment. They were done with at 120 meter and gate watt 100 nanosecond. And so and they are multiple spectrum. You can see the reproducibility is very good. Here is the spectrum of sulfur and gypsum. So as you see, because both have sulfur in it, but because their binding is different, the sulfur spectrum looks very different than the of the gypsum spectrum. This is calcium sulfate with 2 water molecules. So you can easily see, well, this is sulfur and this is the gypsum. Ammonium nitrate, there's also, you can see the nitrate band here, and then there are the lattice modes. And you can also pick up oxygen and nitrogen from the atmosphere. And so this thing works very well there too. This is a ammonium nitrate of potassium perchlorate at 120 meters. And it shows, as you can expect, they have different winding, different atoms involved. And so there's a change in the Raman spectrum. One of the important things is the Raman lines are very sharp. So that means even if you have mixtures, you will be able to separate out, unlike infrared, the bands are broad and it's kind of difficult to separate out different components. So laser-induced breakdown spectroscopy. This can use all kind of materials, solid, liquid, gases, and artificially prepared samples. So the whole periodic table, and it is on the Army's website. And so it really offers advantage that you can get the chemistry of the samples. So the generally used spectrometer is for ocean optics. And so we compared the ocean optics with our small spectrograph. And can you see here ocean optics? And this is to magnify by 1,000 times to able to see the lines. And so this is a condition. Aluminum double pulse leaves pulse generated 150 nanosecond, 100 millijoule per pulse against 2 spectrum from both system, good reproducibility. And the reason for it is that the ICCD camera, which is very sensitive, We use volume phase holographic grating, direct coupling with the Raman and Lipsch spectrograph. And so that explains the difference in the sensitivity of the two systems. Now, this is a very new things here. That was, we got award from the Applied Spectroscopy Society. Idea was to able to do the Raman and Lipsch with low laser power. And then, so then it means we have to use a remote focus technique. And so here it shows that you are focusing on the target. And the advantage here is that because you are having very close, that means you can have a very small size. And also the solid angle increases, so, and then the beam goes back and you can really analyze it. And this just shows a cartoon that you have a car and then you can have a tractor, because lifts can be useful for agriculture as well. And you can fire a low power laser and you can get a good analysis. So I thought I should show this one. So this is the same Raman spectrograph we use, and then it shows that this is a radio operated car. And so there is some substrate there and the 45-degree folding mirror. And we are looking at the sample on the ground. And so, so what happens is that you get a spectrum here. So we are using like 3 mules of laser power, and the distance is 256 meters. Before, people had measured at 100 meters. They use a very large telescope and very high laser power, like 200 millijoules, 200 millijoules to get the spectrum. So this is really a big improvement, and that's why the Society for Applied Spectroscopy was kind enough to award us for this interesting piece of work. So this is the single pulse, and then you got a double pulse, single laser pulse, blue, and then the red pulse is like 20 shots at 1 second integration time. So you can see in a single pulse, or you can accumulate longer pulses to see these low intensity bands much better. Here is the Raman spectrum of KNO3 from 40 meters with 1 millijoules of laser pulse energy. So this system becomes really very eye safe because the beam going out is expanded and then it's only focused on very close to the target. In the past, it was a problem that it was not very eye safe with the high laser power. So this is the spectrum just showing how you change the distance of the lens from the target. And so you can get the spectrum. So this looks like 100 millimeter was a good reproducibility here in the subset and the intensity of the bands. So this cyclohexane generally used for calibrating Raman spectrometer. And here's a comparison because this is 1 second with the lens and 3 millijoules. And then we had 15 millijoules of pulse and no lens. And you can barely see one of the CH stretching band. So there's a huge improvement in terms of the detectability of the samples. So we also looked at the Lipsch spectrum with the double pulse and see the lifetime of these things. So it looks like hydrogen, nitrogen, oxygen bands last only for a few microseconds. And then say 10 microsecond intensity decreases and 20 microsecond is very, very low. So this is one of those things which you have to take into consideration. And next one is, so in double pulse, what happens is that, so the single pulse, you get certain intensities, but if you use double pulse, then the intensity increases significantly. So that means if you use double pulse system, that means that you can increase the intensity of the Raman, of the Lipsch lines, and then it becomes easier detectable. So you have calcium, and then calcium lines, and then potassium lines, and the oxygen. This is a calcium carbonate. So again, you can see a lot of calcium lines here. and there is small amount of strontium in it, a small amount of magnesium. So interesting part is this will not show up in the Raman spectrum, the trace amount, but you can easily see in the Lipps spectrum. This is another mineral called feldspar. It's a sodium aluminum silicate. And here you can see the difference again in the single pulse and the double pulse method. And the sodium lines show up quite nicely, as well as the other lines as well. So this is just shows the calcite and the albite. We had another spectrometer which is used for the UV. So this 250 to 480 nanometer. So in the UV also the signal enhances significantly. And this is the same thing. Gypsum with 2 water molecules, and then the anhydride with no water molecules. And you can see the hydrogen signal from the water shows up quite strong as compared to the one in the gypsum. Also in the anhydride thing, the one of the small amount you see, that's because of the water in the atmosphere. This just shows the spectrum in the UV range, and again the enhancement is there, and so one can really use the techniques for enhancing the signal. So here's again Lipps spectrum with the double pulse in the 450 to 850 nanometer range with 35 millijoules of the laser power. So here is the standoff time resolved luminescence spectroscopy. Can anybody tell me how much time I have? I'm sorry. Hello?
I think, Dr. Saab, 5-10 minutes, no problem.
10 minutes, okay.
Yeah.
Thank you. So this is really, because the Lipps, the laser-induced fluorescence is really very strong. So we designed a system which is very, very small. It's only weighs about less than a kilogram. And you can do that, and you can extend it range from 355 to 532 nanometer. Here is Ruby. These are the R1 and R2 lines of the Ruby. Ruby has a lifetime in millisecond. So as you can see, this is as we increase the gate width to 10 milliseconds, it shows up quite strongly. 100 milliseconds, it shows up almost equal the same thing. So the Ruby, you can measure the chromium fluorescence. Actually, it is the same for all the minerals which have chromium in it. So as the example of biological sample, egg cells, chicken egg cells, they have Raman spectrum of calcite. So the calcite, and it's in the matrix of a protein. So here you can see the fluorescence, broad fluorescence, and there's a Raman spectrum of the calcite. But as you increase the delay, the spectrum gets lower and then it disappears completely. But then what happens is at 135 nanosecond, you start seeing these two humps, which are from the protein matrix. And then you can see the intensity of these changes. So they are two different fluorescence tag in the protein. And so they show up at different time. And then of course it goes flat. So, and this is bottom is the Raman shift. So they're 2003 and delta wave numbers and 3936, 38 wave numbers. So in summary, the combined Raman, Lipps, and laser-induced fluorescence system have been developed at UH. The combined system is only one laser, one telescope, and one spectrograph, and one ICCD detector. Data collected with the instruments are playing important role in March 2020 mission with SuperCam. A combination of these remote sensing techniques are capable of identifying both the minerals and elemental signature of the geological samples and presence of trace transition in rare earth metal ions and biogenic materials in minerals. LIPS technique is a powerful tool when used to reveal the subsurface elemental mineral structure. Consequently, surface minerals can be removed and that may interfere with the Raman probe, remove weather surface, revealing the nascent subsurface minerals, or provide a depth profile of the sample. Double pulse LIPS offer a high signal to noise in the spectrum. Combined Raman laser-induced fluorescence LIPS should have used in many other research areas, including deep ocean, remote in-situ analysis, volcanic lava, and detection of hazardous chemicals in the environment. Thank you very much for your attention.
Thank you very much, Dr. Sharma. Such a nice lecture. I think nobody has such type of information about Mars, because your equipment is working at such a distance and giving such a accurate information. Only one thing I just want to ask this thing, whether you got any other peak of some element which is not existing on Earth there on your this spectrograph.
No, actually the elements are synthesized by the sun, by the fusion, and so they are universally the same on every planet. The rocks are the same, the volcanoes are the same. Mm-hmm. The only difference is we don't know if the life evolved only on Earth or it was evolved somewhere else. So that is a big question. So on Earth, you can get some of the these microorganisms embedded in minerals, and you can see the dinosaurs left bones and all that. But so they're looking at the history and say, is Mars may have evolved some kind of microorganism, and they may still be there. So that is the big question. And that's why NASA is spending a lot of time and effort to figure it out.
Dr. Sreetarthan?
Yes, sir. Thank you so much, sir. It was excellent talk. And I think what else could we have done on National Science Day, because it is really related to Raman and C. We are very proud that our Indian, that is Dr. Shiv Kumar Sharma sir's equipment is working on Mars. It's a great pride for all Indians. Thank you so much, sir, for giving this lecture. Thank you.
Oh, thank you very much for inviting me.
I would like to call.
Can you come for a minute on the camera, because people will like to see you.
Yeah.
Yeah, I think it went back without any problem, so that is good. Can you see me?
Just try. Oh, yes.
Yes,
so this is nice to see you.
Oh, yeah. Thank you.
Thank you, sir.
Yeah, I've been on Zoom for almost 2 years. I haven't left Hawaii because of the COVID. Okay. So yeah. So that is, I think it's true for everybody. Yeah.
Thank you
so
so much.
You are again invited to Amity whenever you are coming to India. Okay.
Yeah.
Sir, can we have a few words from Dr. Ajit Nagpal, sir? Sir, can you please
say it again? I'm sorry.
Sir, actually, Dr. Ajit Nagpal is also there. He's
God bless.
Yes, sir.
Certainly, this is not my field of interest in terms of my academics, but definitely every word that Professor Shiv Sharma said, I imbibed it. And we are thinking that what can be there in other planets. He said that except for life, we are very similar. So it's a very inspiring presentation, and I would say that most of us who are there have been listening to him very carefully and looking forward, because Hawaii it's an area. You see, I'm from my graduation is from US. So frankly speaking, when I was in Boston in Harvard, I actually visited Hawaii. And
I see.
Beautiful islands. And so looking at you and the background also with the university's pictures, I'm reminded of good old days of almost 5 decades So I think it's a very interesting presentation, and most of us who are present here must have enjoyed every bit of it. And certainly, as Professor Sunita Ratan said that, and Professor Jain said that we look forward to your visit to India and come and meet our students and bless them with what you achieved in life. Thank you so very much.
Oh, thank you so much. I think I worked in Washington, D.C., and they invited me to Hawaii, and this place in winter, and this place looks very good. So that's how I moved here in 1980. So yeah, the Hawaii is really a special place. Yeah, thank you. Yeah, yeah.
The life takes you where the destiny is. Yes.
Yeah, sure. Yeah.
Dr. Jain,
Thank
if you
you.
permit, can we have vote of thanks now?
Yeah, I think we are thankful to Dr. Sharma. Now, Dr. Abhishek will present a vote of thanks.
Official vote, right.
Okay, thank you.
Thank you so much.
Yeah, thank you. Thank you very much. So, Honorable Respected Vice Chancellor Professor Babindu Shukla Ma'am, Guest of Honor Professor Shiv Kumar Sharma Sir, Distinguished Professor V.K. Jain Sir, Dean Faculty Science and Technology Professor Sunita Ratan Ma'am, distinguished panelists, faculties, and my dear participants. So, with the blessings of our Founder President Sir, constant support of Honorable Chancellor Sir, and the guidance from Vice Chancellor Ma'am, all the institutes from Engineering, Science, and Technology are jointly organizing the National Science Day. It is my great privilege to welcome everyone in such an event, which is celebrated as a mark of discovery of Raman effect by Indian physicist, Nobel Prize awardee, Shri C.V. Raman. Our Honorable Founder President Sir always believed that we, the Indians, have the intelligence, talent, and potential to be the more successful people in the world. And this marvelous talk from Professor Shiv Kumar Sharma Sir has proven it further. It's a matter of great pride that his developed equipment on Raman effect as a part of the SuperCam instrument on NASA's Perseverance Mars rover is working successfully on Martian land. We usually work with a few centimeters in our instruments, in our laboratories. However, he did it with more than 150, in fact, 200 meters. That's a great achievement, sir. I hope, in fact, that this talk must be very helpful and informative to all the attendees, especially to our students of science, engineering, and technology domain. I would like to thank our guest of honor, Professor Shiv Kumar Sharma Sarji, for sparing his valuable time with us and sharing lots of information, his experiences, expertise, in spite of 15 hours of the time zone variations between us. I am glad that he is an honorary professor of AIARS, Amity University. The objective of this event is spread and share the latest knowledge and wonderful material characterization tool in the field of Raman spectroscopy. Today's program consists of many invited talks from eminent speakers, presentations by research scholars, debate competitions, quizzes, etc., which will be delivered in parallel session. The success of this event depends on effort of many people. Though I cannot thank everyone enough for their involvement and their willingness to take on the completion of tasks, the management and staff of Amity University deserves our special thanks for their support. Special thanks to Professor Sunita Ratan Ma'am, Professor V.K. Jain Sir, who took the vital task of steering this event. My thanks, special thanks to all the eminent faculties for their initiatives and parallel support, especially to all the heads of our institutes, ASSET, nanotechnology, biotechnology, food technology, forensic science, nuclear science and technology. I will also like to thank all the faculties, scholars, students for joining the event. Last but not the least, I would like to thank Amity iMagic Design Center and our best IT support under the leadership of Dr. Sodhi sir for providing perfect online platform. Thank you. Thank you very much, sir. Thank you, all of you.
Thank you. Thank you so much.
Thank you,
Now,
sir.
I think we all can go for our respective tracks. Yes, sir. Please go ahead, Manpreet.
Thank you, sir. We'll now have 4 parallel tracks with various events where we will have lectures by eminent scientists and presentations and competitions by the students. We request you to join the sessions and learn and participate on the celebration of National Science Day. Thank you.
Thank you so much.